Now we're going to talk about standing waves in air columns. And first of all, I would like to start out by reminding to you that we can describe sound waves either using displacement or pressure. For displacement, we had s of xt, the wave function is s max cosine kx minus omega t. And for the pressure description, delta P as a function of x and t is delta P max sine kx minus omega t. Now, if you have a pipe open at both ends, you can set up standing waves from sound. And the reason you can do that is because there is a change in character. So, character of the medium. So remember, if I go from a light string to a heavy string, there is a change in the character of the medium, and some of the waves will get reflected, because when I look at these two sides, going from inside the column to outside the column, the medium character changes. The density of air is, for example, changing. There is a small change in humidity increase, etc. So there is a medium change, and therefore we see reflection of the waves on ends, and these reflected waves and transmitted waves coming from one end will interfere and produce standing waves. So we have to note that wave reflection occurs at an open end due to the change in the character of the medium. It's just like going from a heavy string to a light string or vice versa. So we have to basically discuss what are the boundary conditions for sound waves if I have such a situation. So if I have an air column with both ends open, so if this is cylindrical, let's say, column, and I have both ends open, then the pressure at these 2 points are air pressure, because they're connected to outside. So the pressure is fixed at both ends. So fixed pressure, that means we're going to have no delta P. Delta P must be 0 for standing waves. And that means we're going to have a pressure node. But because I have this phase difference delta phi, pi over 2, between displacement and pressure, if you have a pressure node, that means you have a displacement antinode. All right, so we're now describing the situation in terms of displacement. So here I have a displacement antinode, and for the fundamental mode here, I have antinode, node, antinode. And if you remember, the distance between two consecutive antinodes is going to be given by lambda over 2 here. It's the distance between two antinodes. So I find that lambda 1 over 2 is equal to L. So lambda 1 is 2L. So this is the first harmonic, or the so-called fundamental mode. Fundamental. And I see the corresponding frequency will be the speed of sound divided by lambda 1, so it will be V over 2L. When I go to the second harmonic, I have to start with a displacement antinode and with a displacement antinode. A and A was the first harmonic fundamental. Now I go to the second A. So here I have lambda over 2, and here is another lambda over 2. So the total length should be a wavelength. So lambda 2 for the second harmonic should be L. So F2 is V over 2L, which if I compare with F1, I find that it's twice F1. And if I continue to the third harmonic, then I have A and A first harmonic, and A second harmonic, and A third harmonic, lambda over 2, lambda over 2, lambda over 2. So 3 lambda over 2. 3 lambda over 2 should be equal to L. Therefore, lambda 3 is 2L over 3. The frequency is V divided by 2L over 3, so it's 3V over L. It's 3 times F1. So if I compare this with F1, I notice that it is 3 times F1. So the frequencies are given by Fn is equal to Nv over 2L. N is equal to 1, 2, 3. And Fn is N times F1. So we have a harmonic series for this situation. Now, as I said, we could have equivalently described this in terms of delta P, and then we would say it's a node antinode. Node is the fundamental mode. Now, if I change the boundary condition on one end, so I have pipe closed at two ends. So this was the situation with pipe open at both ends. And now I want to look at the situation pipe closed at one end. Okay, so this time let me draw it here again. This is the open end and this is the closed end, and it's closed. What I see is that the pressure here is fixed. It's the outside air pressure, so delta P has to be 0. So this is a pressure node. On the other hand, here we can have a pressure maximum. So here we have a pressure antinode. Therefore, this is a displacement antinode. And here you can see that I'm not allowing the air molecules to move inside. It's a fixed end. Therefore, this is a displacement node. So once again, I'm using the displacement picture in order to figure out what's going on. So here I take a look at it. The air molecules are allowed to move on the open end, antinode. They're not allowed to move on the closed end. It's a node. So I have an antinode node. So An is my first harmonic, or the fundamental mode. And if I look at the distance between an antinode and a node, I know that this distance is lambda over 4. So I have, therefore, lambda 1 is equal to 4L. F1 is V over lambda 1, V over 4L. Now I go to the second possibility. Now here it's labeled third harmonic. Let's see why it is so. I have to start with an antinode. Antinode. I have to end with a node. So what is the distance between this end and this end? Well, I have lambda over 2, lambda over 4. So the total distance here from this side to this side must be equal to 3 lambda over 4. So lambda 3 is 4L over 3. The frequency is V divided by 4L over 3, 3V over 4L. I see that it is, this frequency is 3 times F1. That's why it's called third harmonic. So it's not the second harmonic. Second harmonic doesn't exist. If I go to the next possibility, I have to start with an antinode and with a node. That was the fundamental. Antinode node, third harmonic, antinode node, fifth harmonic. Why? Let's see. Lambda over 2, lambda over 2, lambda over 4. So I have in total the distance from one end to the other end is equal to 5 lambda over 4. So lambda 5 is 4L over 5. The frequency is 5V over 4L or 5F1. So I find that this frequency is 5F1. All right. So in summary, I find that my frequencies are given by Fn is equal to Nv over 4L, where n is an odd integer, 1, 3, 5, etc. And the wavelengths are given by 4L divided by n, where n is this odd integer. So what is V here? V is the speed of sound. Since this is in air, a speed of sound in air. So basically this summarizes our analysis of this boundary condition. Now one thing I would like to note here is that in both cases we find that frequency is proportional to the speed of sound. So here and also here the frequency is proportional to the speed of sound. And on the other hand, we know that the speed of sound increases with temperature. If you remember, we found that as I increase the temperature, because the average separation between the molecules increase, they have higher kinetic energy and more frequent interaction, the speed of sound increases. And since the frequency of the standing waves here is proportional to V, we find that as T increases, the sound emitted by a flute, gets sharper. So what do we mean by that? It's higher frequency. We're changing the fundamental frequency. On the other hand, if I look at waves on a string in a string instrument, for example piano or violin, etc., the propagation speed of these waves is given by square root T over mu. Frequency is still directly proportional to the propagation speed of the waves, but because we have thermal expansion, as temperature increases due to thermal expansion, the tension on these strings T decreases sharply. So we find that in this case the frequency will decrease instead of increase as in the flute. You may be wondering what happens to mu. Of course, there will be an increase in the length, and therefore it seems to suggest that V should increase and F should increase, but the effect on tension is so dramatic it will dominate the behavior, and basically the frequency we hear will decrease in the case of a string instrument. Now let's take a look at a few examples. A section of drainage culvert 1.23 meters in length makes a howling noise when the wind blows across its open ends. Determine the frequencies of the first three harmonics of the culvert if it is cylindrical in shape and open at both ends. So I have a pipe open at both ends. Open at both ends. I have to say I have a displacement antinode and a displacement antinode on the two ends, because I have a pressure node and a pressure node on the two ends. So these are the boundary conditions for endpoints. Therefore, the fundamental mode is A and A. This is fundamental. So I have a distance from A to A, lambda over 2. So lambda 1 over 2 is equal to the L length. So lambda 1 is 2L. Then I can go to the second harmonic, A and A and A. So lambda over 2, lambda over 2. So I have lambda. Lambda 2 is equal to L. And I can go to the third harmonic, A and A and A and A. Lambda over 2, lambda over 2, lambda over 2. So it's 3 lambda over 2 is equal to L. So that's lambda 3. Lambda 3 is 2L divided by 3. So the corresponding frequencies, F1 is V divided by 2L. Remember, V is equal to lambda F. F2 is V divided by L. F3 is 3V divided by 2L. So Fn is NF1, N is 1, 2, 3. And I would like to know the first three harmonics. So F1 is 343 divided by 2L, 2 times 1.23 meters. So I find this to be 139 Hertz. F2 is twice F1. So I can just calculate twice F1. So this gives me 279 Hertz, roughly. 279 Hertz. F3 is 3 times F1. $278 actually. F3 is 3 times F1, so this will be 417 Hertz. And in part B of the question, what are the three lowest natural frequencies if it's blocked at one end? Okay, so pipe closed at one end. Then I have the following condition. It's going to be a displacement antinode in the open end and displacement node in the closed end, or a pressure node in the open end and a pressure antinode in the closed end because of the phase difference of pi over 2. So AN is the fundamental, and here I have lambda 1 over 4 is equal to L. Lambda 1 is 4L. an, I have to start with an a and with an n. So this is lambda over 2, lambda over 4. So 3 lambda 3 over 4 is equal to L. Lambda 3 is 4L over 3, etc. So I find that lambda n is 4L over n. Frequencies are nv over 4L, where n is an odd integer, 1, 3, 5, etc. So what are the three lowest natural frequencies? So if I find f1, it's going to be v over 4L. So it's 3v over 4L, that is 343 divided by 4 times 1.23, that is 69.7 Hertz. Then I can calculate f3, that is 3 times f1. This will be 209 Hertz. Then I can calculate f5. f5 is 5 times f1, that is 348.5 Hertz. So I can see that these frequencies of the first three harmonics will change if I close one end. Let's look at one more example. A simple apparatus for demonstrating resonance in an air column is depicted in the figure. A vertical pipe open at both ends is partially submerged in water, and a tuning fork vibrating at an unknown frequency is placed near the top of the pipe. The length of the air column can be adjusted by moving the pipe vertically. The sound waves generated by the fork are reinforced when L corresponds to one of the resonance frequencies of the pipe. For a certain pipe, the smallest value of L for which a peak occurs in sound intensity is 9 centimeters. What is the frequency of the tuning fork? What are the values of L for next two resonance conditions? So first of all, I have to understand the boundary conditions here. Clearly here I have a pressure node because it's open air, and here I'm going to get a closed end basically, or it will behave like a closed end because there is a change in the character of the medium, and here I have a pressure antinode. This may be easier to see in terms of displacement because the displacement of air molecules is restricted here. So it's going to be a displacement node, and here I have a displacement antinode. Alright, so that means this is like a pipe open at one end, closed at the other end. So this is a displacement node, and this is a displacement antinode. So I have an lambda over 4, and here I have an, and here I have for the fifth harmonic, third resonance, an. Alright, so the smallest possible value for L for which a peak occurs will correspond to L is equal to lambda 1 over 4. So this is 9 centimeters. Therefore, I find that lambda 1 is 36 centimeters. Lambda 1 is 36 centimeters. So what is the frequency of the tuning fork? V is equal to lambda f. This is in air, so I have the frequency f1 is V divided by lambda 1. It will be 343 divided by 36 centimeters, which is 36 times 10 to minus 2 meters, 950 53 Hertz. So if I convert it to SI units. So this is the frequency, the unknown frequency of the tuning fork. So I know that this is oscillating at a frequency of 953 Hertz. What are the values of L for the next two resonance conditions? So here I have answered part A. In part B, I'm going to change the L and I'm going to try to get the next two resonance conditions. So as we said, AN is the fundamental mode. We have AN, the third harmonic, because here we have lambda over 2 and lambda over 4. 3 lambda 3 over 4 is equal to L, or L prime, because we're changing the resonance condition by changing L. Alright, so does the wavelength change when I change this length of the pipe? So the frequency fixed by the tuning fork. The speed of sound in air, speed of sound is fixed in air. It is 343 meters per second. Since V is equal to lambda F, V is fixed, F is fixed, lambda is fixed. And what is lambda? 36 centimeters. So my next length will be 3 over 4 times 36. So it's going to be 27 centimeters. And for the next resonance condition, I have AN, lambda over 2, lambda over 2, lambda over 4, fifth harmonic. This is going to give me 5 lambda 5 over 4 is equal to L double prime, but lambda 5 is the same as lambda 1. Lambda is not changing, so L double prime is 5 over 4 times 36. This will be 45 centimeters. So the next two resonance conditions will occur when the length of the opening will be 27 centimeters